I've asked you to accept a lot here without actual mathematical proof on this issue of the most probable distribution, and I'm going to go a step further with that now with this video. But I want to say a little bit about how dominant the Boltzmann factor distribution is when talking about these molecular systems. So this is going to be the subject for this video. Now, how would we characterize various distributions? Let's suppose we had a way of graphing different distributions together. And I don't know what you would use to label those distributions somehow, but let's suppose that their probability, was graphed something like this. All right, it's a nice bell-shaped curve distribution, and it's very clear that the most probable distribution would be, so these are over distributions, is our horizontal axis, and probability is somehow graphed on our upper axis. We clearly have a most probable distribution here. It is the one that has the highest value of probability. But if I were to move over just a little bit, say to here, I wouldn't be sacrificing a whole lot in probability. In fact, that probability of that second distribution is pretty close to the probability of the most probable distribution. So the real question that I'm asking here is this the case for these distributions that we've been talking about for molecules? In other words, the distribution that is characterized by these values for the populations, and e to the minus ej over kbt, and if I divide it by n, I'm going to divide by z. So is this distribution like this? That is to say, there are other distributions that are pretty close to having the same sort of profile, or is it something different? Now, the way I want you to think about this, and I'm going to use an example, an analogy to do this, is let's suppose I'm doing an experiment where I'm flipping a bunch of coins, okay, and I'm going to somehow draw a box here where I'm going to record the results of flipping the coins. Now, if I were to flip a coin once, we both understand that there's one half probability it would come up heads and one half that would come up tails. But it's going to be one or the other. It's either going to be heads or it's going to be tails. So I'm going to draw across this axis here, heads on one side and tails on the other. So if it's just one flip, I'm either going to be over here or I'm going to be over here. That's it. If I do two flips, it turns out I'll have 1/4 of the time I'll end up with one head and three tails, or somewhere in here. I'll have half the time I'll get half, and half the time I'll get one tail and three heads. Or maybe this is the other way around. I guess I'm saying it the wrong way. This would be one head and three tails. This would be one tail and one head and three tails. This would be one tail and three heads. All right, we would have something simple like this. A pretty broad distribution if I were to connect this by lines. Now, the more times I flip the coin, it turns out I end up going from a distribution that might be fairly smooth and narrow, but the more times I flip the coins, the more that distribution becomes more sharply peaked, about having half and half. And in fact, if I were to flip that coin 1,000,000 times, I would find that the distribution of heads and tails is very sharp right here in the middle. That with 1,000,000 coin flips, the most probable is going to be 500,000 heads and 500,000 tails. And granted, 499,000 heads and 1,000 tails would still be pretty reasonably probable, but I'm going to have practically none that are 1,000,000 heads and 0 tails. Basically, that's just not going to happen. So the question is, in our distribution that we've found here, this most probable distribution, is it more like a few coin flips or is it like 1,000,000 coin flips? Well, one way we could resolve this would be if we did an experiment. Let's suppose we start with the most probable distribution, the one that we've defined here. And what we want to do is we want to make a small change to that distribution that will keep the same total energy, but will change it so that it is something close to the most probable distribution, but not exactly the most probable distribution. So one way we could do that is out of every 1 million molecules, I'm going to choose 2 of them. And with those 2, I'm going to move up 1 by plus E and 1 down by minus delta E. So in other words, I'm just changing the energy of 1 by up and 1 by down so that the total energy stays the same. All right, and I think we could agree that if we're only changing 2 molecules out of a million, we're not really changing the distribution very much. And I could certainly tune it by making this number bigger and smaller, but I'll just say for a reasonable number, say 1 vibrational quantum, that we've changed this, we've got a distribution that is pretty close to our most probable distribution. Now the question we would ask then is, what would be the ratio of the microstates for our most probable distribution divided by the number of microstates for the nearby distribution? All right, so how much does it change? Are we going to get a number that's close to 1? Because that would tell us that most probable is not very exclusive. Or are we going to get something else? Well, when you use some reasonable numbers in here, and like I said, using like a quantum of vibration, let's say about 3,000 wave numbers of vibrational energy, and this is changing 2 molecules out of every million, all right, so it's a small change, it's a pretty nearby distribution. What does this ratio go to? Well, it turns out you can calculate this out, and one calculation I saw relates it to this. That's 10 raised to the power of 10 to the 11th power. 10 to the 11th is, let's see, 1, oops, don't put a comma there yet, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So here's where the commas go. So it's basically 100 billion, if I've counted those correctly, 100 billion. So 10 raised to the 100 billion power is the ratio of these microstates. What does that mean? Well, it effectively means that the chances of finding a system of molecules that is in this nearby distribution, where only a small change has been made, is practically 0. In fact, it is in effect 0. So that should tell us that in fact the sort of picture we're looking at for molecules is more like this tall, thin one. We've got a very, very probable distribution, and it's so probable that we don't even really need to consider any other distributions. It is the only one that contributes in any meaningful way to the state of a system. So even though I haven't given you a detailed derivation of how we got there, I hope this helps to convince you that we really do have the most probable distribution, and if we have a system that's at thermal equilibrium, that is the distribution it will be in.